Okay, welcome to another Stat 432 video. It's been a while. So the main purpose of this video is to, one, recap what it is we're doing in this series of videos on analyzing the heart diseases data, and two, getting me back into a routine of doing this. Didn't get a lot of things done over break, so here I am, trying to get back into the groove. Okay, so, so basically what I'm going to do is go through some of the stuff we've already done so that me and you know what we're doing, and then to sort of maybe do some new stuff. If not, definitely sort of outline where I'm going a little bit. I think my gain's a little high. Okay, there we go. All right, so let's get started. So first, I'm gonna open up this README. Ooh, I decided to go with a dark theme today for something different. Just trying out different themes in our studio. Okay, so maybe it'll be more instructive to look at the data. So here are the notes that we had been taking, but I'm gonna jump into this file, which is all the code that we've gone through so far. I guess what I'll do is I'm gonna run through this to make sure I remember what it does, and then come back and see what things we can change, reference the notes, and README to sort of get a picture of where it is we're going. I just need to start somewhere, so I'm gonna start running some code. So this code was loading some packages. What do we load? Caret, tidyverse, rpart, and rpart plot. Okay, cool. I think previously we had fit a very simple tree model to this data. All right, so here we go, reading in the data. All right, let's have a look at this. All right, so the main takeaway, if I recall correctly, is that a row of this data is a patient from a hospital, and columns are information about that, such as their age, sex. I forget what some of these things are, so we're going to go look at that in a second. But then, sort of importantly, this num variable here had to do with whether or not the person had heart disease. V0 was our label for no presence of heart disease, and then V1, 2, 3, and I think 4. I forget exactly what it was counting, but those were severity of heart disease. But basically, V0 is no heart disease, V1 through V4 is increasing severity of heart disease. And then the location was the hospital where the data originated from. Okay, cool. Going back to the README real quick, our notes. We had sort of been talking about these. Okay, so CP was the chest pain type. Resting blood pressure, cholesterol, fasting blood sugar. I don't know why this is like that. There's a change. EKG results, heart rate achieved in a stress test, exercise. Okay, did you get chest pain when exercising? Something about some measurement based on a stress test, something based on a stress test. This variable we still weren't really sure on, but I don't think we were going to use anyway for reasons we'll talk about in a second. Okay. That's funny because that's copied out of the document. But anyway, this was a variable about whether or not your heart was normal or not. For example, you could have a defect that was fixed or a reversible defect that was not fixed. Okay, and this num was presence of heart disease. Okay. So let's go back here. I'm going to save this. Okay. So the very first thing we did was we test train split the data. So here are our training datas. Here are our testing datas. And then we changed a lot of things to be factors. For example, the heart disease, those were categories. The locations, obviously categories, whether or not you have chest pain category, and so on and so forth. So let's run. And I notice that I'm doing this in the training data because I'm really like, I really even In some ways, I wish I hadn't even seen this data. I'm really trying to not do anything with the test data, even things like determining which variables are factors. I want to do it, and I don't think that's really important, but I want to do it based on only the training data. So I'm going to have to come back and do this to the test data later. But we haven't looked at the test data. We're not going to until the very end. So, right. Okay. We had discovered that there were all these zeros in the cholesterol data, which we realized that's not a possible cholesterol value, so we set those to NAs. Then what I did was look at proportion of NAs. So in the training data, it looks like, if I remember right, the cholesterol variable, the fasting blood sugar variable, there was another one, and the slope variable. Oh no, those are not even the bad ones. These are the bad ones. Slope, CA, and thal. To address this again, I think especially, okay, so this CA variable, what is it, right? It's number of major blood vessels colored by a fluoroscopy. Anyway, I'm not 100% sure what this variable is because I'm not a medical professional, but what I think it is one of two things. It's either they did some general injection of like a medium that would get picked up on some sort of testing machinery, and it's a number of things that showed up. But it's also, what I think this is, if I'm reading it correctly, is like the hospital decided, oh, we're going to color these blood vessels and see if then we can see them in our imaging. But sort of either way, if our whole point here is to make a screening model that would be able to be ran with input data that is not difficult to collect, this is either a practitioner decided number or something that's really hard to obtain. So I'm fine leaving that out. This thal variable, I kind of think that there's kind of a couple issues with it, right? So the issue is that, one, we don't have this data on a lot of people because the only way we would have this information is if they had already gone through extensive testing, because you don't know if your heart is normal until someone looks at it, right? I have a lot of personal experience with this. I went like nearly 30 years in my life thinking my heart was totally normal, and then one day I went to the doctor, and a lot of testing later I learned that it is not normal. So this is something that you either went through a ton of testing to get this information, or you don't have it. So it's either costly to obtain this information, or more likely we don't have it. So that's another variable that makes a ton of sense to just not include here. And again, I know this seems like I'm spending way too much time on like variables than models, but I'm doing that on purpose because I think it's important. Lastly, this slope variable. So this slope variable here, it has 30% missing data. That's a lot. And ultimately, I think we would like to not have to use the stress test variables, because that means that to use this method, we would have to put people through a stress test. But if we were going to put them through a stress test, it would be nice to include this variable. But I think for now, we're going to remove it. So what we had previously determined is that we were going to remove anything with more than 30% missing. So the variable we're going to have to contest with the most at the end is this cholesterol variable, because actually, let's do something real quick. I don't think we've done this before. Okay, so I'm going to do that. So now what I'm going to do is I'm going to recheck. Oops. Okay, so... Oh, that's unfortunate. So what I was hoping is that... Oh no, I'm removing columns, not rows. Never mind. I didn't need to do this because nothing was going to change. Okay, anyway. A little bit of this. I'm realizing now that if I just jump to this, I wouldn't have needed to write that function and do that thing, but you live and you learn. This was just us summarizing the data again. Okay, good. Okay. And if I remember right, this plot was how we identified all those 0 cholesterol values, although now you don't see it, so that's good. Okay, and we could still go back and spend a ton of time looking at plots and graphics and seeing if we can find stuff like that. We might, but for now I want to keep going. Okay, so one of the big things that I want to do is talk about missing data. Because again, if we go back here, let's look at this. We have 738 training observations, right? Which is, in 2020, it's probably not a lot of data. Would I want to, just with that number alone, 738 observations, would I want to, even if this model seems pretty good, would I want to release this out into the wild and say, hey, everyone use this, screen all your patients with this? Probably not. That would probably make me really nervous because, this was only collected at 5 places. It was seemingly patients that were already going to the hospital from what we can tell, and we only have about 700 of them. Worse yet is that currently we have a bunch of missing data here. And our current strategy is going to be lazy, and we're just going to ignore the missing data, which brings down the amount of training samples that we have. Not super great. This is us. I'm going to even write that in. To do. Don't do this. It is being lazy. But for now, we're going to do that just because I want to see what modeling we had done, and then we'll circle back. I think this is going to become our next big issue, and I think it'll be the next video and the biggest one. But I'm going to have to introduce some new concepts for that, so that's going to be a little bit more in depth. Okay, but now we're dealing with a data set that does not have any missing data anymore. It looks kind of like this. I don't know why I did that, but importantly, because we removed all that information, so all those rows were down to only 500 and some training observations. And if we think about this, this cholesterol variable, we also could consider simply removing it, but that seems to be a useful thing that's not too difficult to acquire. And realistically, if I had the cholesterol data, I probably have a bunch of other blood testing data that I could put into this that we just don't have access to. So I think we'd want to push to keep that. So my ultimate goal is to leave this in, but we're going to need to deal with that. Okay. Right. Okay. So what do we do next? Okay. So for some reason... okay. So this was just me testing if we could... get some baselines and fit some models, but I'm going to sort of skip that. Okay. So it looks like what we did here. Aha. So this was introducing carrot. So I'm going to work through this again. Okay, so this is what we already did. This was a note along the way that we already did. I'm going to make this come out with this. Set up 5 full cross validation. Okay. So it looks like we were going to tune a tree with these values of that parameter. We were going to tune k nearest neighbors where it tries k from 1 to 100. And it looks like we were also going to tune a boosted tree model. Okay. So these are setting up the parameters we're going to tune over. So in particular, if we look at this boosted tree model, so this is one tuning setup. So using 500 trees, they're going to be very shallow trees, a certain shrinkage, and a certain, this is a tree parameter, min observations per node. Not important, but basically each row here represents a set of tuning parameters that are going to be tried for that model. So for example, here we are fitting the tree model. Shouldn't take too long. Fitting the k-nearest neighbors model. Going to take a little bit longer. And fitting the GBM model. This should take a while. Well, relative to the previous two. Okay, cool. Oh, and also here, I'm fitting a random forest, but I'm using the default parameters that caret selects. Okay. So if I were right, what I'm doing here is I'm showing. I remember. So this is what. Okay. Show how easy it is to use caret. That was the point of this, showing that the predict function works the same way for any of the possible models. So for example, I think if I change this to class, it'll produce, okay, raw. At least it's a helpful error message. But the point is that the way you do it is the same with each of the models. Okay. Not important, but I'll leave it like this. Okay, so I think something we didn't do last time, I don't remember, but a good thing to look at is, let's look at the performance of these things. So here are the models. So, okay, this tree model. So here we have, for the different values of the tuning parameters, a cross-validated accuracy. And it looks like this value of the tuning parameter, which is here, produced the highest cross-validated accuracy for the tree model. I'm going to do something that I shouldn't do, but I'm going to do that. Okay, for the k-nearest neighbors model, let's see. K equals 65 was the best, which is right here. And that got this cross-validated accuracy. Let's look at the GBM model. This might be a little more difficult to find. Okay, so 150 trees. Interaction depth of 1, shrinkage of 0.1. Is it this one? That looks close enough for government work. Yeah, so that was our best value there. Then let's look at the random forest. So I didn't give it any tuning information here, but it tried. So generally what it does by default is a very low value, a very high value, and then something in the middle. And depending on its classification, how it determines this one's different. But anyway, I can see very quickly that this is what we get. Okay, so a few things here. So if we look at these, we would say that, okay, this boosted model is the best, right? Right off the bat. Just if we want to go with highest cross-validated accuracy, okay, that's the best model. But a lot of questions to ask ourselves. This is a complicated model, a rather complicated model, actually. It's actually a lot of trees sequenced together so it's a sequence of trees. This is a very simple model with, is there really a difference between these two numbers in practice? I don't know. So what I mean by that is I think I can do rpart.plot. Oh, I need to do, aha. So if we look at this, CP, what is CP4? What variable is this? Just a second. HD tree mod. Can I get the, oh no, that's not gonna do it. Oh, CP is a, oh, there's different type. Okay, so, okay, cool. All right, so I thought it was a yes, no, but it's different categories. So I don't know what type of chest pain this is, but okay, so this is great. So, oh, this leads back to my note right here. change levels of the factor variables for understanding. So rather than 4 here, I should go into the documentation, figure out what 4 is, and then actually apply that to the data. Maybe I'll do that next time. Okay, but anyway, something we haven't really talked about. We'll add this to our to-dos. Model interpretability. I can't spell. Did I spell that right? Close enough. So something we haven't talked about a lot is model interpretability. And that's a whole topic unto itself. People have written entire books about this, entire courses on this. It's kind of a hot topic in machine learning right now. I think its importance ranks sort of right under making sure like you're using the right methods for the right goal and understanding all of that. And then after that kind of comes interpretability. Because at the end of the day, if we frame things correctly as a prediction problem and only care about prediction, knowing exactly what's happening inside of a black box model, black box model, that is an opaque box that you can't see into. Is opaque the right word, or is that the opposite word? Anyway, a box that you can't see inside of. But often we would, especially as humans, we would feel more comfortable knowing sort of why a model is making the decisions it's making. And we can see that right here, right? So this model is very clear what it's doing. It's saying, okay, so if you have this type of chest pain, here are the probabilities that you end up in the different groups. So by and large, you would not have heart disease if you have that type of chest pain. And then, you can follow this chart. So that's one way of looking at it, is that we understand why. I mean, why is the wrong word there, kind of. But like we can see how our model is making its predictions. Yeah, definitely how, not why. Why was the wrong word. But even better than that, to use the boosted model, I would have to train hospital workers in some new piece of software, which, let's be honest, it's 2020. That wouldn't be that hard. We write the software, we ship it, although we would have to work with the medical software providers and all that and get it licensed and all that. Or alternatively, I suggest that with no statistics training, little mathematics training, if I make this plot a little bit nicer, I could hand it to anyone in the hospital, from the doctor to a nurse to anyone working in that hospital, even the patient almost, and teach them to follow this flowchart that says, okay, I have this type of chest pain, I'm at this location, I have this cholesterol, and here's my result. I submit that trees are some of the most interpretable models around. They're very easy to understand. You don't need statistics training to understand it. Granted, the way this particular graphic looks, I wouldn't want to share it with a non-technical person, but we could clean this up and make it much easier to understand. So what I'm getting at is that even though these two models have similar performance, this one has a huge benefit, and that it's very simple from an understanding perspective, which can be useful. So what would I trade off this 1.5% or 2%, whatever it is? Maybe. The next thing we need to think about is this the metric that we care about? Is accuracy what matters here? So let's investigate here a little bit. So I think I can do this. Aha, here we go. So what I have here is a cross-validated confusion matrix. So what this says is, averaged over the 5 different confusion matrices that would have been created in a 5-fold cross-validation, it looks like 47% of the time, the person did not have heart disease, and we predicted they didn't have heart disease. These are also good predictions, nothing here. Okay, right? So now let's look at this a couple other ways. So of the people without heart disease, the vast majority of them we labeled as not having heart disease. These folks here, this is an error now, right? So they didn't have heart disease. We said they did, but the least severe amount of heart disease. Same thing here, even fewer. Same thing here, even fewer, but increasing in severity. So if we're going to make a mistake, making a mistake here is a lot better than making a mistake here. I think. I'm not a medical professional. I don't know a lot about cardiology, but that would be my guess. Although realistically, I think all these errors are this error, this error, and this error, and this error are not great. But because our whole sort of idea here is we want to create a screening procedure, these errors, this one, this one, this one, and this one, are not the end of the world because this is just a screening. So then they would go on for more detailed testing, the invasive procedures where they, inject things into you, run, do all sorts of crazy stuff. Okay, great. Now let's look at the other errors that are being made. So for example, if we confine ourselves to this column here, okay, so these are people that have heart disease, and here we're making the correct prediction. This is a wrong prediction, but realistically, okay, so you have this level of heart disease. We predicted a slightly more severe heart disease. Well, that ain't the end of the world, because once we labeled you as having heart disease, you probably would have gone for additional testing anyway to confirm it. So that's fine. Same thing here. This is where the problem is. This is what we don't want to see. So that is, this is actually really bad too, if you think about it, right? So let's just say, let's pretend that this, and this doesn't exist, and 12.2 and 12.4 are very similar. So that's saying of the people that have this severity of heart disease, we predict half of them to have heart disease and half of them to not have heart disease. Nope, that's not acceptable. Let's go to the extreme now over here, right? So this is the worst level of heart disease we see in this data set. We predict none of it correctly. None of it. Here, and here. Those are all mistakes in the classification problem as stated, but at least we're saying that heart disease is present. Not to the extent that it truly is, but at least we're catching it. This is a problem. So here, we're saying, okay, so of the folks with the worst possible severity of heart disease, we're missing a certain fraction of them. I don't know, within the column what the proportion is, but it's non-trivial, very clear. It's like almost a quarter of the cases, it would seem. Now, we don't have a ton of data in here, so that's a little unreliable, but we don't like that. So I'm curious, though, how this compares to the GBM model. So I sort of flippantly said, there's not a big difference here. But if this number is significantly smaller for GBM, I'm going to like it a lot more. Let's have a look at that. That's not what I wanted to do. I wanted to do this. Like that. Aha! So, while the difference in overall accuracy is not big to me, this is great, right? So not only are we making some correct predictions here, we're doing much better here. But actually, let's... sorry, I'm just getting these to where I can reference them back and forth real quick. It looks like we got worse in this column here. Like there's nothing here. There's some stuff here. But we did better in this column. So there's a higher percentage here than here. So what I'm getting at here is there's two potential mistakes we can make. We can, for someone that does not actually have heart disease, say they have heart disease and they go for additional testing. Or someone who has heart disease, we can mistakenly label them as not having heart disease, and they go about their life not knowing they have heart disease. So what we really like to do is, instead of tuning these models for accuracy, we need to tune them for minimizing, I think in my opinion, these errors, up here, maybe at the expense of having a few more of these here. Right. So that's something we need to do. And I think I need to look at my notes now and think about what I mentioned. Okay. Change levels of factor variables. Okay, we mentioned that. Look into negative values of old peak. I think we said we were going to ignore that. Deal with missing data. So that's going to be, I'm putting this up here as it's high priority. Okay. Fit and evaluate models. Establish baselines. That's kind of what we're doing right now. So like, for example, it's, getting above an accuracy of like 60%, we should be able to do. Consider moving. Okay. So this is also high priority. So instead of considering these different severities, we can just smash that down and say, okay, this is heart disease. This is one category that doesn't have heart disease. So then, this plus 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 this. Okay. Basically, we can get it down to a binary classification problem, and we can consider sensitivity and specificity. Do we care more about false positives or false negatives? And then we can go back and we can use a different metric in the tuning algorithm. So instead of trying a bunch of different tuning parameters and picking the one with the best accuracy, we can try a bunch of different tuning parameters and pick the one with the best, say, sensitivity or specificity, depending on how we define false positives and false negatives. Okay, so in dealing with missing data, we're going to do that as a part of the fitting procedure, and I'll say sort of why. We did this a little bit already. For this analysis, we're not going to do any models beyond the ones we already have, except for we're gonna this one we haven't done yet. Okay, so we need to add a linear model in there. So I'd like to do a logistic when we get it down to binary. We started doing this. That'll be something we do. I did spell this wrong. Interpret. Whatever, close enough. Right. Okay, so okay, so in summary, our main charge. To do summary 1, missing data. That's gonna be our big thing. 2, binary classification. I'm gonna put binary in quotes because I'm gonna add a wrinkle to that when we do it. And then 3, use more appropriate metric for model selection. Okay, so that's gonna be our next 3 big focuses. I'm gonna say missing data and other pre-processing. Because I guess right now I think it's safe to say that it's safe to say that K-nearest neighbors is not performing well here. I want to make an attempt at making that better, and that'll have to do with some pre-processing. Tell me that. Okay, it's spelled right. Okay, so feels good to just click record and make a video. All right, so actually, I don't know which one of these I should do next, but the next video is either going to be dealing with the missing data or getting this down to a binary problem and using a different metric. Maybe I'll do it all at once, but that would be a ridiculous video. But either way, hopefully that refocuses you. It has refreshed my memory about what we're doing. I know I've been putting off this missing data thing for a while, but I think I'm there now. There's nothing else we can do except for one of these 2 things. So I'm going to try to get back to my just click record once a day and just record whatever it is I do on these things so you can see what's going on here. Okay, so that was probably a rather unfocused and rambly video, but it's a style. All right, so as always, if you made it to the video, good job, and I will see you in the next one.